So here's our problem. A merry-go-round of mass 115 kilograms and radius 2 meters spins at 2.6 radians per second, while a 65 kilogram student stands at the edge. Find the new angular speed after the student has moved to a distance of 0.5 meters from the axis. So we're going to use the idea of conservation of angular momentum, where the final angular momentum must equal the initial angular momentum. Specifically, that means that the final moment of inertia times the final angular speed must equal the initial angular momentum times the initial angular speed. So let's find the initial angular momentum first. Now to do that, we need the initial moment of inertia of the system, which is equal to the moment of inertia of the merry-go-round plus the moment of inertia of the student. That quantity multiplied by the initial angular speed. So we're going to go to our table of equations for moment of inertia, and for a disk, a uniform disk of mass m and radius r, the moment of inertia for that disk spinning about its center is 1/2 mr squared. We're going to consider the student to be a point mass that's a certain distance from the rotational axis, mr squared. Again, these equations here and here are from a table of moments of inertia values, where we're considering the merry-go-round to be a uniform disk spinning about its center, and we're considering the student to be a point mass at a distance r from the center. All of these values we know. We know the mass of the merry-go-round, we know its radius, we know how far away the student is from the center, we know the mass of the student, and we know the initial angular speed. That number comes out to be 1274 kilogram meters squared per second. That initial angular momentum is numerically equal to the final angular momentum. But here's what's going to happen. This student in the upper right is now going to move closer to the axis. Instead of being 2 meters away, this student is only 1/2 meter away. So let's calculate the new moment of inertia. There's the moment of inertia of the merry-go-round. That hasn't changed. But the moment of inertia of the student has changed. Instead of being 2 meters from the axis, he's only 1/2 meter from the axis. So the equation is still mr squared, but the r is different now. If we simplify this as much as we can, we get 246.25 times the final angular speed. Well, those two quantities, by the law of conservation of angular momentum, are numerically equal to each other. So if we simply set those equal to each other and solve for the final angular speed, we get 5.2 radians per second, which we can see is larger than our initial angular speed of 2.6 radians per second, and that's what we would expect if the moment of inertia decreases, then the angular speed would have to increase.